Let's look at the gamma distribution. For example, suppose people call a 911 center according to a Poisson process at the rate of 15 calls per hour. Find the probability that we need to wait more than 5 minutes for the first call. We did this kind of problem earlier. Let x be the waiting time until the first call. Recall that x has an exponential distribution with mean theta equals 1 over lambda, where lambda is the mean number of calls per hour. And again, this is because if you have a Poisson process, then the gap between events has an exponential distribution. X has p.d.f. f of x equals 1 over theta e to the negative x over theta. The mean of the waiting time, x, is mu equals 1 over lambda, which is theta. The variance is theta squared, and the moment generating function is 1 over 1 minus theta t. Let's convert everything to minutes. We don't want to have hours and minutes. So lambda is the number of calls per minute, which is a fourth, because again, if you get on average 15 calls per hour, that means you'll get a call every 4 minutes, which means you get a fourth of a call per minute. X has p.d.f. 1 over theta e to the negative x over theta. That's 1/4 e to the negative x over 4. Because again, if lambda is a fourth, theta is the reciprocal, which is 4. The probability that x is greater than 5 is the integral from 5 to infinity of f of x. In this case, that's 5 to infinity of 1/4 e to the negative x over 4. The integral from 5 to infinity 1/4 e to the negative x over 4 dx. So let's go ahead and integrate this. The antiderivative of 1/4 e to the negative x over 4 is 1/4 e to the negative x over 4 over negative 1/4, because that's the constant that's next to the x in the exponent. And we evaluate that at infinity and at 5. When you plug in infinity, you get 0. When you plug it in at 5, you get negative e to the negative 5/4. So the answer is e to the negative 5/4, which is 0.2865. Now find the probability that the waiting time for the third call is less than 20 minutes. Okay, now in the problem we just did, we were waiting for the first call. Well, the waiting time for the first call, that has an exponential distribution. The waiting time for the third call, that's going to have a gamma distribution. So in general, let x be the waiting time until the alphth call. X has a gamma distribution with p.d.f. f of x equals 1 over gamma of alpha, theta to the alpha, x to the alpha minus 1, e to the negative x over theta, where gamma of alpha equals the integral from 0 to infinity, y to the alpha minus 1, e to the negative y dy. Whoa, that looks like a nasty integral. But mercifully, gamma of alpha is simply alpha minus 1 factorial, when alpha is a positive integer, which is alpha minus 1 when alpha is a positive integer. So it's usually easy to calculate gamma of alpha. In general, gamma of alpha is alpha minus 1 factorial. The mean of the waiting time, x, is mu equals alpha theta. The variance is alpha theta squared, and the moment generating function is 1 over 1 minus theta t raised to the alpha. Notice that the mean makes sense. If the average waiting time for the first call is theta, then the average wait for alpha calls would be alpha theta, alpha times theta. Okay, in this problem, alpha is 3. We're waiting for the third call. Theta is 1 over lambda, which is 1 over 1/4, which is 4. And gamma of alpha is gamma of 3, and that's going to be 3 minus 1 factorial, which is 2 factorial, which is 2. So f of x is 1 over gamma of alpha, theta to the alpha, x to the alpha minus 1 e to the negative x over theta. In other words, it's going to be 1 over gamma of 3, 4 cubed, x to the 3 minus 1 e to the negative x over 4. But since gamma of 3 is just 2 factorial, which is 2, and 4 cubed is 64, we end up with 1 over 128 x squared e to the negative x over 4. So the probability that x is less than 20 is the integral from 0 to 20 of f of x dx. So that's the integral from 0 to 20 of 1/28 x squared e to the negative x over 4 dx. And that's 0.8753 if you use f and int on the TI. You could also integrate that by parts, but we're not going to. Now I'll find the probability that the waiting time for the 15th call is longer than 1 hour. In this problem, alpha is 15, gamma is 1 over theta, which in other words is 4, and gamma of alpha is gamma of 15, which is 14 factorial. So f of x, when you plug in everything, it's going to be 1 over gamma of 15, 4 to the 15th, that's theta to the alpha, x to the 15 minus 1 times e to the negative x over 4. Holy cow, that is 1 over 14 factorial. 4 to the 15th, x to the 14, e to the negative x over 4. So the probability that x is greater than 60 is the integral from 60 to infinity, f of x dx. So that's, in other words, the integral from 60 to infinity, 1 over 14 factorial, 4 to the 15th, x to the 14, e to the negative x over 4. And that's 0.4657 if you use f(n)ins on the TI. Of course, the TI doesn't have an infinity button, so you have to replace infinity with a sufficiently large number. Okay, now let's find the mean of the waiting time for the 15th call. Well, the mean for the waiting time, that's just going to be alpha theta. In other words, it's 15 times 4, which is 60. How about the variance? The variance of the so find the standard deviation of the waiting time for the 15th call. Well, the variance of the waiting time is alpha theta squared. In other words, 15 times 16, or 240. So the standard deviation is square root 240. Okay, now we're ready to do this problem. 2015 SOA Sample Exam P, problem 57. An actuary determines that the claim size for a certain class of accidents is a random variable x with moment generating function m sub x of t equals 1 over 1 minus 2500 t to the fourth. Calculate the standard deviation of the claim size for this claim of accidents, for this class of accidents. We did this one earlier, but now we can solve it much more quickly. The function m sub x of t equals 1 over 1 minus 2500 t to the fourth is the moment generating function for a variable that has a gamma distribution with theta equals 2500, alpha equals 4. The variance is just alpha theta squared. In other words, 4 times 2500 squared, which is 25 million. So the standard deviation is the square root of 25 million, which is 5,000. And the answer is thus B. The moral of the story, it's worth memorizing. It's worth knowing the moment generating functions for certain kinds of variables.